Imagine pointing your phone at a room, and a photorealistic 3D world builds itself in real time, instantly, even on a standard laptop. Welcome to our podcast, Artificial Intelligence, Papers and Concepts, curated by Dr. Satya Malik.
I mean, it sounds like science fiction, honestly, but it is exactly what we are digging into today.
Right, and before we really get rolling here, I should casually mention that both of the voices guiding you through this conversation today are entirely AI-generated.
Yeah, completely artificial.
But don't let that stop you from leaning in, because our mission for this deep dive is, well, it's absolutely fascinating.
It really is. We are unpacking a brand new paper. It's called ReCoSplat, autoregressive feed-forward Gaussian splatting, using render and compare.
Which is a mouthful.
It is, but it comes from this massive collaborative team across UC Merced, ETH Zurich, NVIDIA, Shanghai Jiao Tong University, and HKIST.
And the goal today for you, the learner, is to figure out exactly how AI is learning to reconstruct 3D environments from streaming 2D images.
Right on the fly.
Exactly. Taking messy, real-world sequential photos like a library bookshelf or a kitchen sink and turning those into full 3D maps instantly.
And doing it without needing a massive supercomputer to handle the math.
Which is the crazy part. But before we get into the brand new solutions this paper proposes, we probably need to define the core concept for everyone.
Good idea.
The title mentions Gaussian splatting. What exactly is a Gaussian splat? And, how does it differ from the standard 3D graphics most of us are used to seeing?
So that's the perfect place to start. For decades, when computers built 3D worlds, think of video games or architectural software, they used wireframe meshes.
Right, like polygons.
Exactly. They built objects out of thousands of tiny, rigid triangles. Gaussian splatting kind of throws that old playbook right out the window.
Okay, so no more triangle.
No more triangle.
Oh, okay.
Instead of hard geometric shapes, it represents 3D space using millions of tiny, overlapping, fuzzy-colored blobs. Yeah, mathematically, these blobs are defined as Gaussians. And because they're continuous and slightly transparent at the edges, they blend together to create these incredibly photorealistic, lighting-accurate scenes.
And I'm guessing they render much faster than complex mesh models.
Way faster.
Okay, so we're painting with millions of fuzzy 3D math blobs. That makes sense. But the paper focuses on doing this autoregressively. Why is that such a big deal?
Well, it comes down to how the AI actually learns the space. Traditionally, Gaussian splatting requires this really lengthy offline training.
Meaning it needs all the answers up front.
Right. The AI needs to be handed a folder containing every single photo of a room from every possible angle before it even begins calculating where to place those fuzzy blobs.
It has to analyze the entire data set globally.
Exactly. But think about real-world applications. If you have a drone navigating a collapsed building, or, you're wearing an AR headset and just walking into a new room.
The AI doesn't have the luxury of seeing the whole environment ahead of time.
Exactly. It has to process the visual data autoregressively.
Meaning sequentially, one frame at a time as the camera feeds them in.
Correct. It has to build the 3D world live, making decisions about where to place those splats based only on the limited sequential glimpses it has received so far.
Which honestly sounds incredibly difficult. But before we look at the massive headache this creates for the AI when trying to process images live, I want to quickly mention that this podcast is sponsored by BigVision.ai, a consulting and product development company that helps companies of all sizes build computer vision and AI solutions. You can reach them at contact@bigvision.ai.
So getting back into that headache.
Right. So we have this challenge of building a 3D space on the fly. If the AI is just getting random snapshots from a camera feed, how does it know where to put those images in the larger 3D space? It seems like it would just get lost immediately.
And it does. This is what the researchers call the assembly pose dilemma.
Okay, let's unpack this. What is an assembly pose?
When the AI receives a single local image, it has to figure out its assembly pose. That means estimating the exact location and angle of the camera when that specific picture was taken.
So it can anchor that local image into the global 3D coordinate system it's trying to build.
Precisely.
It's sort of like trying to build a jigsaw puzzle while you are walking around a room. If you have a perfect map of your footsteps, placing the puzzle piece is easy.
Yeah.
But if you're just guessing your steps, putting the piece down in the right spot becomes really difficult.
That analogy captures the problem perfectly. Because in laboratory training environments, researchers give the AI perfect maps of those footsteps.
The cheat sheet.
Exactly. They provide exact, known camera locations, which the paper refers to as ground truth poses. And in trained on ground truth poses, the AI learns beautifully. It figures out exactly how to turn 2D pixels into 3D Gaussians.
But I'm guessing that doesn't work when you take the AI out of the lab.
It fails spectacularly. Yeah, because in the real world, there are no ground truth poses. The AI has to rely on its own internal estimates, which are known as predicted poses.
And those predictions are going to be a little off.
Right. They are inherently noisy and imperfect. So a phenomenon occurs called a pose distribution mismatch. The AI encounters positional noise it literally never saw during its pristine laboratory training.
So it panics.
Basically. The Gaussians become misaligned, the math breaks down, and the 3D reconstruction just turns into a blurry, unusable mess.
Well, then why not just train the AI on messy, noisy data from the start? Just let it learn with the predicted poses so it's ready for the real world.
Other models have definitely tried that, but this paper notes it causes severe instability during the training process itself.
Why is that?
If you couple the task of learning what an object looks like with the task of guessing where the camera is randomly pointing, the network struggles to converge. You are asking it to solve two massive moving variables at the exact same time.
So training with perfect data fails in the real world, but training with messy data crashes the training process. That feels like an impossible catch-22.
It really is a tricky problem.
How does the ReCoSplat team actually fix this?
They introduced a mechanism called the render and compare module, or the ReCo module for short.
ReCo. Render and compare.
Right. It relies on an established concept in computer vision called analysis by synthesis. The core idea is that you refine your predictions by comparing what you synthesize or create against what you actually observe.
Wait, let me pause you there. If the ReCo module is pausing to synthesize and render a 3D scene every time a new image comes in, doesn't that slow the whole process down?
Yeah.
I thought the ultimate goal here was real-time speed on consumer hardware.
It sounds counterintuitive, I know, but the rendering of Gaussian splats is computationally lightweight compared to the heavy lifting of predicting the geometry from scratch.
Oh, I see.
The slight pause to render is a necessary trade-off to ensure accuracy. And as we'll see later, they found other ways to drastically speed up the pipeline to keep it real-time.
Okay, so walk me through how this module actually works when a new image arrives.
When the AI receives a new 2D frame, it doesn't just immediately try to guess new 3D Gaussians. First, it looks at its current accumulated 3D scene, everything it has built so far.
It's working memory of the room.
Right. It then renders a 2D snapshot of that 3D scene from the viewpoint it predicts the new camera is sitting at. Finally, it places that internal rendering side by side with the actual incoming real-world image.
Okay, I think I'm following. It's like walking in a dark room, guessing your location based on your memory of the space, turning on a flashlight to see what's actually in front of you, and then immediately correcting your mental map based on the difference between what you expected to see and what the flashlight reveals.
The flashlight analogy hits the nail on the head. By generating this rendered observed pair, the module isolates the exact discrepancy caused by the camera pose error.
It spots the difference.
Exactly. The network then uses this comparison as a stable conditioning signal to guide the rest of the process. It does this via a mechanism called cross-attention.
We hear the term attention a lot in AI, usually with text models like ChatGPT. What does cross-attention mean in the context of visual AI fixing a 3D map?
Think of cross-attention as a matching process. It allows the neural network to look at two different sequences of data, in this case, the features of the rendered image and the features of the observed image, and mathematically calculate which parts of one sequence are most relevant to the other.
Like finding the overlap.
Yes. It essentially asks, which pixels in my internal render correspond to the pixels in this real-world photo, and how far shifted are they?
Oh, wow.
This alignment tells the system exactly how to adjust the new Gaussians to compensate for the fact that its camera pose guess was slightly off.
That makes a lot of sense. It's actively looking for the shift between expectation and reality.
And to make this cross-attention signal even richer, the researchers went a step further. They didn't just rely on comparing standard red, green, and blue colors.
They added more data.
They augmented each of those fuzzy Gaussian blobs with 9 extra learned feature dimensions specifically for appearance.
What does that mean? Extra learned feature dimensions. Why isn't color and shape enough?
The researchers ran ablations to figure that out. An ablation is simply a test where you remove parts of an AI system to see what breaks, which proves what is actually necessary.
like pulling out Jenga blocks.
Exactly. They tried running the ReCo module using only geometric data, specifically testing something called plucker ray maps, which just encode the geometric paths of the camera rays.
And it didn't work.
It failed. The geometric data alone couldn't consistently correct the pose-induced reconstruction errors.
So they needed those appearance features.
Right. By adding 9 abstract AI-learned dimensions that capture complex appearance variations, like how light reflects differently depending on the angle, they gave the model the deeper context it needed to bridge the gap and fix its mistakes on the fly.
That is wild. It's learning abstract visual properties we don't even have words for, just to help it align the room.
It really is brilliant.
So the ReCo module solves the alignment problem, which is incredible. But reading through the paper, that brings us to the second massive hurdle. And honestly, this one feels like the biggest practical roadblock: memory.
The memory bottleneck is usually what kills autoregressive 3D generation.
The paper mentions that processing hundreds of sequential frames through a multi-view transformer backbone, in this case, an architecture called Pi3, causes a computer's VRAM, its video memory, to absolutely explode.
It skyrockets.
Before we talk about how they fixed it, what is a transformer doing here, and what is a token in visual AI? I know text tokens are like syllables of words, but how do you tokenize a photograph?
To process an image through a transformer, the AI chops the photograph up into a grid of tiny square patches. Each patch is converted into a mathematical representation called a visual token.
Like cutting a photo into a mosaic.
Yes. So instead of reading a sentence word by word, the transformer reads the image patch by patch. The transformer's job is to analyze the relationships between all those patches to understand the context of the scene.
And to do that, across multiple images sequentially, it has to remember the old patches. The paper mentions something called the KV cache.
The key value, or KV cache, acts as the AI's short-term memory. In autoregressive models, to make sense of a new frame, the AI needs to remember the context of the tokens it has already seen.
So it stores them in the cache.
It stores this memory in the KV cache. But when you are processing high-resolution images across a sequence of dozens or hundreds of frames, and each frame has thousands of these token patches, the sheer volume of data multiplies exponentially.
I can see how that gets out of hand fast.
A standard GPU simply runs out of memory. This triggers an O, or out-of-memory error, and the entire program crashes.
Right. And nobody's walking around with a liquid-cooled server farm in their backpack when they were trying to scan a living room with an AR headset.
Exactly.
So how did the ReCoSplat team compress this data without losing the quality of the 3D map?
They engineered a highly sophisticated two-part hybrid KV cache compression strategy. The first part is called early layer truncation.
Early layer truncation.
The Pi3 transformer backbone they use operates through 18 distinct processing steps, or layers of global attention. The researchers recognize a crucial pattern in how visual AI works.
Which is?
The early layers of the network are mostly just extracting local features. They are looking at things like sharp edges, textures, and solid colors within a single isolated image.
Let me guess. Because they are only looking at the current image, they don't need to reference the memory of the old images.
You've got it. Multi-view correspondences, understanding how an object in frame 1 relates to an object in frame 50, doesn't happen until the deeper layers of the network.
Well, that's clever.
Because of this, the researchers simply discarded the KV cache entirely for the first 10 of those 18 layers. They essentially told the AI, don't bother remembering anything for the first half of your processing.
Just cutting out the first 10 layers of memory entirely. That alone has to save a staggering amount of space.
It makes a massive difference.
But what about the remaining 8 layers that actually do need the historical context to map the 3D space?
That is where part 2 comes in. Chunk-level selective retention. Instead of trying to force the model to remember every single frame it has ever seen, they process the incoming video feed in small chunks, usually 4 to 8 images at a time.
Okay, small batches.
Within that small chunk, all the views attend to each other, sharing information and building localized 3D context. But when it's time to move on to the next set of images, the AI doesn't keep all the tokens from the previous chunk in the long-term KV cache.
It throws them out.
It drops almost all of them, retaining only the tokens from the very last view of the chunk.
So it's basically taking a summary snapshot. Is that last view acting like a compressed zip file of the previous 7 images?
Conceptually, yes. The network learns to pack the most important geometric and contextual data from the entire chunk into the representations of that final frame.
That is fascinating.
And to ensure the network actually knows how to uncompress and use the summarized data later, they mark that final retained view with a trainable register token.
A register token.
It acts as a flag, signaling to the network, this isn't just one photo. This contains the synthesized memory of an entire past sequence.
Does it do that for the very first images it sees too? I'd imagine the beginning of the scan is pretty important.
There is one vital exception, and you just hit on it. The very first chunk of 8 images is kept entirely intact in the memory.
To lay the groundwork.
This is crucial to safely anchor the initial scene representation, giving the AI a solid, high-fidelity foundation to build the rest of the map upon.
The paper lays out the impact of this two-part compression strategy, and the statistics are incredible. For a sequence of 256 images, a standard uncompressed KV cache would need to store 4,608 token sets.
It is a massive load.
But with ReCoSplat strategy, it stores only 312. That is an over 90% reduction in memory usage.
It's game-changing.
We're talking about the difference between requiring a massive multi-GPU research cluster and being able to run real-time 3D reconstruction on a standard consumer graphics card like an RTX 4090.
It fundamentally democratizes the technology. It moves autoregressive 3D generation out of heavily funded corporate laboratories and makes it deployable in real-world edge devices.
And the researchers proved this viability through their testing methodologies. They didn't just use perfect, meticulously captured laboratory datasets to validate ReCoSplat.
No, they didn't.
Let's talk about that real-world testing.
Yeah.
They evaluated this in the wild. I saw they used a dataset called ScanNet++O, which involves room-scale indoor scenes.
Yeah.
If you actually look at the source data for ScanNet++O, it is full of incredibly blurry, shaky visual scans of ordinary, cluttered things.
It's very realistic.
It's a random desk with a monitor, a hallway with a water fountain, a messy kitchen sink, or a library bookshelf where a large potted plant is partially blocking the camera's view. And the images are uncalibrated and totally unposed.
That irregular, chaotic camera movement is exactly what breaks most online reconstruction models. When a human walks around a room waving a smartphone, the motion is entirely unpredictable.
Lots of sudden pans and motion blur.
Exactly. Yet, ReCoSplat tackled ScanNet++ beautifully.
What about outdoor environments? A kitchen sink is one thing, but sweeping landscapes are a different challenge.
They evaluated it there, too. They used Real Estate 10K, which features diverse indoor and outdoor walkthroughs, and another dataset called ACID, which is composed of outdoor aerial drone videos of coastlines and terrain.
Coastlines and terrain?
Yeah.
That's a huge scale shift.
What's particularly crucial about the ACID dataset testing is that ReCoSplat had never even seen that data during its training phase.
So it was a completely out-of-distribution test. It was asked to map an environment entirely different from what it learned on, and it still worked.
It excelled. Across all these diverse input settings, whether the inputs were fully posed with known camera data, completely unposed, calibrated, or uncalibrated, ReCoSplat achieved state-of-the-art results. It beat out previous strong baselines in the field, like FreeSplat and S3POGS, and the internal metrics prove why it won. The render and compare module successfully isolated and fixed the pose distribution mismatch on the fly, while the hybrid KV cache ensured the system didn't bog down and crash.
It just kept running smoothly.
It made the model incredibly robust. Even when the AI's initial guess was completely off due to a shaky camera movement, the ReCo module allowed it to self-correct in real time, matching or even exceeding the performance of offline models that had the unfair advantage of seeing all the images in advance.
So, bringing this all back to you, the listener, what does this actually mean for you? Why should you care about Gaussian splatting, early layer truncation, and assembly poses?
It's a fair question.
Because this research bridges a critical gap in consumer technology. It means the dream of holding up your phone and instantly mapping your living room for an augmented reality game is rapidly becoming a reality.
Absolutely.
It means a first responder drone could seamlessly navigate a collapsed building, mapping a disaster zone in real time for rescue workers, relying only on sequential, messy 2D camera glimpses.
And, importantly, it can do all of this locally on the device without needing to upload gigabytes of private video feed to a cloud server farm. The AI builds the world as it sees it, intelligently correcting its own steps along the way. This capability raises a fascinating implication, and it's a thought I really want to leave you with today.
I'm intrigued.
If an AI can now compress and reconstruct robust, photorealistic 3D environments from sequential, messy 2D glimpses on the fly, what does this mean for our own digital memories?
Our memories.
We have spent the last century capturing flat 2D photos and videos, but with technology like ReCoSplat running on standard consumer hardware, we might soon be moving from scrolling through flat photo albums on a screen to literally stepping inside a real-time 3D spatial memory of our past experiences.
That is an incredible visual.
A fully immersive, explorable 3D environment built entirely from a few shaky smartphone videos you took years ago.
Imagine walking back through a 3D memory of your childhood home, generated instantly from an old home video. That is an incredible thought to end on. Thank you so much for joining us for this deep dive into RecoSplat. We hope you found these concepts as exciting as we did. If you enjoyed this conversation, please hit subscribe so you never miss an update, and we will see you on the next one.